Hi everybody, this is vCPU scheduling and SQL Server and potentially Oracle database performance. My name is David Klee. I'm a certified nerd. I love this stuff. I'm lucky to be a Microsoft MVP and a VMware vExpert, which means I get some really interesting insight into where both of these companies are going with the platforms. I started my own company 3 years ago, Heraflux Technologies, to really focus on how these two data stacks really come together: infrastructure, virtualization, cloud, and data. And what you're going to get is just a taste of a lot of the tech that I normally charge people for with our consulting practice. First of all, we all know that inside the hypervisor, we have scheduling queues for how to have the VM send things to the vCPUs and how it actually gets to the physical compute resources. Everything in there, the four major food groups, CPU, memory, network, disk, all of those have their own schedulers per VM. And what we need to figure out is what happens when things are not set up properly. What's dependent inside the VM? How do these things balance with the physical machine? Well, I'm going to focus most on CPU because that is one of the biggest, most silent performance killers that you're ever going to see in these very large database systems. Our goal is to minimize queue waits. Anything spent in the queue is time not spent running, and as a result, these very critical, latency-sensitive applications, such as big database servers, slow things down. Time spent in the queue is time not spent actually running. If it's not running, that's a big performance impact. And a file server, print server, web server, whatever, you know, the impact is a little more minimal. With these things are very large, they're very resource intensive, and any small impact or misconfiguration further down the stack, it impacts the performance pretty significantly. Every single thing in that VM must be scheduled to go through these queues, and as a result, we have to make sure that the time spent there is at least possible, or the lowest possible. This also includes idle resources, including CPUs that are not actively being used, which is why we got to right-size these things. So if you haven't seen it before, that's a server. That's what a lot of this stuff runs on. Inside the server is a motherboard. Guess what? This is where the CPUs, memory, backplane, network adapters, things like that all plug into. This is called NUMA, non-uniform memory access. A while back, AMD pioneered it, Intel perfected it, and what they found was that the interconnect between CPU and memory became a bottleneck. What they ended up doing was finding a way to take the memory and actually put it very close to each one of the CPU sockets. Well, if it's very close and the workload is confined right there, you have a performance bump. If not, there's a problem. So this is that same motherboard. That is one NUMA node, or associated CPU socket, and its memory that's local. Well, what happens when I have an application that I need to run fast? If the CPU here needs to fetch memory from one of the other NUMA nodes, guess what? Physics dictates that that takes forever in terms of memory. It's still nanoseconds, it's still really fast, but it's over a 3 times performance penalty than if we have to fetch it locally. So the hardware ended up taking this awareness and extending it into the physical machine layer into the operating system. So you as a developer can say, if my application can run in that one NUMA node, all the memory lookups are guaranteed to be local and I have the potential for a significant performance improvement. Well, the virtualization layer can extend this proximity into the virtual machine. And guess what? These very large database servers can pick up on this and make internal optimizations themselves and get even faster. What we got to do is figure out how to size these things properly to fit the physical CPU topology. First of all, we need to figure out how many CPUs we need. And guess what? Just because the vendor says you need 64 doesn't mean you need that. Just because the developers are asking for more than you have doesn't mean they need it. You have to objectively prove with numbers, with performance data inside the guest, inside the database engine. You have to go see what they're actually using and consuming, and then you can go spot check what you need. And it's not just a 2-hour point in time. I mean, we're talking like weeks of profiling to go figure this stuff out. And then, if it'll fit, I want to build that VM to fit inside one physical NUMA node. So equal or less than number of CPUs than what exists there. Same thing with RAM. If it fits comfortably, the hypervisor, ESXi, is going to do a really good job of trying to pin that thing in one NUMA node. Otherwise, balance this thing. And I can't tell you the right configuration there because it's all different. There's background activity, there's different workload characteristics, there's different hardware types, but you can test this. You can test it very, very easily. So, for example, what if I asked you that I needed a 16 vCPU VM? What's better? 2-socket by 8-core VM, 4x4, 8x2, 16x1, 1x16? What's better? Standard DBA answer, any DBA is going to tell you this. It depends. It all matters on what the physical infrastructure and what the background, all that stuff. But you can test this. Now, DBAs really should have a good ability to take a production workload, profile it, back up the database in a test system, and then replay the workload. You know, load runner, distributed replay, all these other utilities. If they work, they can replay the workload as if it were an actual production machine. And then guess what? You go change the CPU configuration, you can test it. If they don't have that methodology in place, well, they should, but if they don't, you can actually use some synthetic benchmarks. This is HammerDB. Free, open source, test Oracle, SQL Server, MySQL, Postgres, and MariaDB, and it works really well. You create a sample database and then you throw a synthetic workload on it. Under different virtual CPU configurations, this is the net impact of what it actually does. That is upwards of a 31% performance improvement under that particular workload intensity. Well, the challenge there is this right for all workloads? Guaranteed not. Because in this case, the graph here ends at 256 worker threads. That was the official number that we got. Well, if you notice, the 4x4 came out on top. This was a 4-socket, 10-core physical machine. Well, at 1,024 worker threads, when I went back that night and tested it again, the 2x8 actually came out on top. The hypervisor ended up prioritizing, and the NUMA locality was much better than 4x4 under exceptional load. Windows also managed it better because it only had 2 NUMA nodes to worry about instead of 4, and then the database server was able to handle it better as well. So again, workload intensity matters as well as all this other stuff. Fun part, test it. Find the right configuration that works for you. This is what happens when you get it wrong. That is CPU ready time on a 16-core virtual machine. And guess what? Half the cores were on a local NUMA node, even though the VM didn't know it, and half the cores were running 20% slower than the other half. The database engine in this case was parallelizing everything across the board, and guess what? The database server is actually about 40% slower than they expected. We went in and we changed it from 1x16 to 2x8. We actually didn't drop the core count, and magically the problem just went away and everything got faster. It was 4 clicks to figure that out. It's not bad. They've been fighting that for 2 months. Easy to spot here. It's hidden from inside the VM. Now, why does this matter? Let's say I've got SQL Server that's dumping workloads into a single virtual socket VM. If this thing doesn't align right, 16-core VM, well, when the hypervisor goes to distribute that load on the CPUs, guess what? It's throwing stuff everywhere. And that's not necessarily optimal. It's going to try to balance it, but there's more activity there than what that one socket can keep up with. If I balance this thing properly and I actually instruct SQL Server to instruct or to issue the queries on just one NUMA node's worth of CPUs, it will balance itself. So we issue the same load, and guess what? Those CPUs are now active. All the memory on the NUMA node and all the CPUs are local to one node. On average, we see a 30 to 40% performance improvement in 4 clicks. Just by balancing, just by a little bit of CPU architecture and just understanding how the physical realm, the virtual realm, and the database server come back together. So, in conclusion, 1, you got to right-size this thing, and you can't do it just once. You have to do it at least every quarter. If it's really active, do it more frequently. Databases get added, reports get added, more users get added, more data gets added. We all have to fight that all the time. So, right-size it frequently. Balance it with the physical NUMA, balance it with the virtual NUMA, monitor the heck out of it, monitor scheduling queues, ready time and co-stop, and if you want to talk more about those, come see me, I'll be right back here. And then afterwards, just watch the performance, because guess what? You just squeezed a lot more performance out of a lemon right there, and it's going to work great. Thanks a lot, everybody.